KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, now we start with the 18th problem. So it is additional exercise. So the problem number 18th from our textbook. Okay, right. So in this class we will focus on these problems what we had, that is what 18 to 21, 18, 19, 20, 21. Right. See here. See the problem 18th. First I will read the problem. Listen. Two towers on the top of two hills. Two towers on the top of two hills are 40 kilometers apart. The line joining them passes 50 meters above a hill. The line joining them passes 50 meters above a hill, halfway between the towers. Right? I will repeat once again. The line joining them passes 50 meters, right? Passes 50 meters above a hill, halfway between the towers. Full stop. What is the longest wavelength of radio waves? What is the longest wavelength of radio waves? What is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effects? Between the towers without appreciable diffraction effects. Right? So I will repeat once again the whole problem. You just concentrate. Two towers on the top two hills. Just you have to imagine, here is one hill, here is another hill, right? So like that you have to imagine. Two towers on the top of two hills are 40 kilometers apart. The line joining them passes 50 meters above. The line joining them passes 50 meters above a hill. Halfway between the towers. Okay, right, full stop. What is the longest wavelength of radio waves? What is the longest wavelength of radio waves which can be sent? What is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effects? Okay, right. So that's what we have to find. We have to find the wavelengths. Okay, ma? Right. See here. See this. Here, the size of the Fresnel distance. Size of the Fresnel distance, that is what size of the Fresnel's zone. Size of the Fresnel's zone, AF at the middle hill must be less than 50 meters. Must be less than 50 meters. That is what they have given now. That is what 50 meters above a hill, right? So according to this information, it should be less than 50 meters. So that distance of either of the two hills from the middle hill, that is what 20 kilometers now. You know that the distance between the two towers is 40 kilometers according to the given information, right? Middle hill means it is 20 kilometers from either of the tower, right? So it is 20 kilometers means 20,000 meters. Now see here, size of Fresnel's zone, that is what AF is equal to square root of lambda d, square root of lambda d, right? So that's what you know the formula. From that formula we are writing, right? So it is size of the Fresnel's zone AF is equal to square root of lambda d. So according to this information, whatever we told here, whatever I told here, that is what therefore square root of lambda d must be less than 50 meters. No, just for this information the mathematical form is this one, right? That is what square root of lambda d is double less than, right, 50. See this. So just you are squaring on both the sides. No, it is what lambda d double less than 2500 or lambda is less than or equal to 2500 by d, 2500 by d. This is what lambda value. Okay, then lambda is less than or equal to 2500 by 20,000, 2500 by 20,000. Okay, then what will happen? These two zeros will get cancelled. No, so 25 1, 25 4. Then finally is what 1 by 4, right? See here, observe carefully. Sorry, 1 by 8 will come because 25 4 is 100. No, but here we had 200, so 1 by 8. So 1 by 8 means 0.125. So lambda is double less than 0.125 meters. That's you can write in centimeters. It is 12.5 centimeters. 12.5 centimeters. You know the wavelengths longer than 12.5 centimeters will undergo appreciable diffraction effects, right? So he is asking what is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effects. So according to this, you know the wavelengths longer than 12.5 centimeters will undergo appreciable diffraction effects. Okay, right. Next, see here, it is what next question, which is what 19th question. See here, next question. A parallel beam of light of wavelength 500 nanometers falls on a narrow slit and the resulting diffraction pattern is observed on a screen 1 meter away. It is observed that the first minimum is at a distance of 2.5 millimeters. It is observed that the first minimum is at a distance of 2.5 millimeters from the center of the screen. Right? So find the wavelength of the slit. Find the width of the slit. Right? So slit means width only. Generally wavelength means for light. So whatever the experiment we used, whatever the experiment we did, that is what diffraction experiment. There he is asking what is the width of the slit. Okay, right. See this. A parallel beam of light of wavelength 500 nanometer falls on a narrow slit and the resulting diffraction pattern is observed on a screen 1 meter away. 1 meter away, right? That is what 1 meter is like capital D, right? So capital D is the distance between the slits and the screen. No, that is what he is asking to find width of the slit. And one more value, that is what 2.5 mm. 2.5 mm is the distance minimum. First minimum is at a distance of 2.5 mm. So it is what x1, because first minimum no. So it is x1. x1 is equal to 2.5 mm, that you can write it as 2.5 into 10 to the power of minus 3 meter. And wavelength of light, that is what, 500 nanometers. So that 500 nanometers you can write it as 5 into 10 to the power of minus 7 meters. 5 into 10 to the power of minus 7 meters. Okay. So based on the given values, the values what they have given, wavelength of light as 500 nanometers, if you convert into meters it will be 5 into 10 to the power of minus 7 meter. And next one is capital D, it is the distance between the slits and the screen, it is 1 meter. And the distance of your first minimum, which is what, x1 is equal to 2.5 mm, that is equal to 2.5 into 10 to the power of minus 3. 2.5 into 10 to the power of minus 3 meters. It is what x1 is equal to, right? Okay. As x1 is equal to, capital D lambda by small a. Capital D lambda by small a. So from this, what is small a? Small a is equal to d lambda by x1. D lambda by x1, right? So what is d? 1. What is lambda? 5 into 10 to the power of minus 7. 5 into 10 to the power of minus 7. That is what lambda. Okay. Divided by x1 is what? 2.5 into 10 to the power of minus 3. x1 is 2.5 into 10 to the power of minus 3, that is. So you do this calculation mathematically, then you will get it as 2 into 10 to the power of minus 4. 2 into 10 to the power of minus 4 meters. Okay. 2 into 10 to the power of minus 4 meters. Okay. 2 into 10 to the power of minus 4 meters. Okay. Right. See here. Next problem here only. It is 2 into 10 to the power of minus 4 meters, means you can write it as 0.2 meters. No, sorry, 0.2 millimeters. 0.2 millimeters, right? Okay. So after completion of this, you can go for next question, which is what, 20th question. It is like a theoretical question. You just concentrate here, and he is asking the reason. Okay, right. So answer the following questions, right? So there are two questions. First we are going for A, and then we are going for B. See this. See here, first A. When a low flying aircraft passes overhead, we sometimes notice a slight shaking of the picture of we sometimes notice a slight shaking of the picture on our TV screen. Okay. So he is giving the thing, what happens naturally, what happens actually, and asking the reason, right? So what is the situation he has given? That is what, when a low flying aircraft passes overhead, we sometimes notice a slight shaking of the picture, on our TV screen, right? Full stop. Suggest a possible explanation, right? So that is what he has given the reason, and he is asking the explanation. Next, see here. See the solution, right? First we will finish A, and then we will go for B, right? Because now only I read the question now, so you can remember the information what is there in the question easily. So that I am going for answer. See here. When a low flying aircraft reflects the TV signals, when a low flying aircraft reflects the TV signals, right? Due to the interference, when a low flying aircraft reflects the TV signals, due to interference between the direct signal received by the antenna, and the reflected signal, right? we sometimes observe slight shaking of the picture, slight shaking of the picture on the TV screen, slight shaking of the picture on the TV screen, right? That is what, see here, when a low flying aircraft reflects the TV signals, when a low flying aircraft reflects the TV signals, due to the interference between the direct signal received by the antenna and the reflected signal, due to the interference between the direct signal received by the antenna and that is what weak reflected signal. So it is weak, that's why he kept in the bracket weak. We sometimes observe slight shaking of the picture on the TV screen, right? As simple as such, the reason here is interference of, right, interference between direct signal received by the antenna and the reflected signal, right? So this is the reason for A. Now see here, we are going to check B. See this. As you have learned in the text, the principle of linear superposition of wave displacements is basic to understanding intensity distributions. In diffraction and interference patterns. Okay, right, full stop. What is the justification of this principle? Right? Okay. So here first B. So A completed, now B. See here. As you have learnt in the text, the principle of linear superposition of wave displacements is basic to understanding intensity distributions in diffraction and interference pattern. So what is the justification of this principle, right? So he is telling the information and he is asking the justification. Okay. So in the text itself, the principle of linear superposition of wave displacement is a basic to understanding intensity distributions in diffraction and interference pattern. So what is the justification of this principle? Okay, right. See this. What is superposition principle? We know, superposition principle follows from the linear character. Superposition principle, right? Superposition principle follows the linear character of the equation. That is what the differential equation follows from the linear character of the equation. Governing means like driving, governing wave motion, right? So he is telling the importance of superposition principle. That is what the superposition principle follows from the linear character of the equation. Governing wave motion, right? Okay. If y1 and y2 are solutions of the wave equation, right? So is any linear combinations of y1 and y2, any linear combinations of y1 and y2. When the amplitudes are large, for example, high intensity laser beams and non-linear effects become important, the situation is far more complicated. Right? So what he is saying here, first thing is, superposition principle follows from the linear character of the equation governing wave motion. That is what equation of wave motion, right? Okay. If y1 and y2 are the solutions of wave equations, suppose for example there are two waves, for one wave it is what y1 and another one it is y2, right? Understood, For one wave it is y1, like y is equal to a sin omega t, like that we are writing wave equation. Suppose for one wave it is y1 and for another wave it is y2. So that's why he is saying that y1, y2 are solutions of the wave equation. So, in any linear combination, that is what, so is any linear combinations of y1 and y2, correct, full stop. When the amplitudes are large, that is what, high intensity laser beam and a non-linear effects, right. So, when the amplitudes are large and non-linear effects become more important. So, in this situation, these are important. So, the situation is far more complicated. So, in case of high intensity laser beams, the situation is far more complicated. Okay, right. Next, 21st. Okay, next question. See here. In deriving the single slit diffraction pattern, it was stated that the intensity is 0. At angles of n lambda by a. In deriving the single slit diffraction pattern, it was stated that the intensity is 0 at angles of n lambda by a, full stop. Justify this by suitably dividing the slit. To bring out the cancellation. Okay. So, he is asking to justify, right. Okay. See here. So, what he is saying, in deriving the single slit diffraction pattern, it was stated that the intensity is 0 at angles of n lambda by. Okay, anyhow, theta is equal to n lambda by a. That's it. Theta is equal to n lambda by a. So, where the intensity is 0, right. Justify this by suitably dividing the slit to bring out the cancellation, right. So, he is asking like proof. Okay, but it is a small thing. See here. Divide the single slit into n smaller slits of width a dash. Divide the single slit into n smaller slits of width a dash is equal to a by n. So, this we got it from our discussion, that is what, a theory discussion, right. So, where we discuss now, that is what, in case of single slit diffraction, there we came to know. So, they suppose if the slit is going to separate into n number of small parts, so what is the width of each slit, like that. So, divide the single slit into n smaller slits of width a dash is equal to a by n. Next, then itself angle is equal to, so already he told theta is equal to n lambda by a. So, this n lambda by a, you can write lambda by a dash, no. N lambda by a means you just take this one also. So, in place of a, you can write a dash into n, right. So, n will get cancelled, lambda by a dash, theta is equal to lambda by a dash. Okay, right. See here, each of smaller slits sends 0 intensity in the direction theta. Each of the smaller slits sends 0 intensity in the direction theta, full stop. The combination gives 0 intensity as well, right. The combination gives 0 intensity as well, and this is the angle, that is what, theta is equal to lambda by a dash. Okay. So, this is what he is saying, right. So, observe carefully. Okay. In this class, we discussed 4 problems, right, 18, 19, 20, 21. Okay, right. And this is the last class. So, for wave optics, numericals, this is the last class. Okay. In the next class, we will continue with another chapter. Okay, but this is the last class. See here. So, in 18th problem, he asked to find size of the Fresnel's zone. The formula is AF is equal to square root of lambda d. But he is asking, right. Okay, first size of the Fresnel zone, okay, but there itself he is asking what is the longest wavelength of radio waves which can be sent what is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effects, okay, right. So in second problem he is asking what is the width of the slit, okay, that's what. Next question, it is what, the 20th question. You know, in first case he is asking when low flying aircraft passes overhead, right, so the TV screen is going to shake, what is the reason? Next, B is, see here, so the principle of linear superposition of wave displacements is basic understanding of intensity distribution in diffraction. So how can you justify this statement, that he is asking, okay, right. So in the next problem, it is what, in the last problem, so he is asking justification for the situation, that is what, in case of single slit diffraction pattern, it was stated that the intensity is 0 at an angles n lambda by a. Otherwise, in terms of a dash, you know, according to this statement, this information, which is theta is equal to lambda by a dash, okay, right. So this is all about 4 problems, okay. So we will continue in the next class with next chapter.